SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process from Lord Buddha, who says, just as candle cannot burn without fire, men cannot live without a spiritual life. It is really a very profound statement, which is missing in our day to day life, as we are not bothered about the spiritual aspect of human life. In the last lecture, we discussed about stationary flame method for determination of burning velocity, and in which we looked at three methods. Basically, one is very sophisticated method of measuring local burning velocity using PIV or particle image velocimetry. Other is a little simpler, but crude as compared to the sophisticated method. Other two methods which are being routinely used in the laboratory are the area method and the nozzle method. So, today we will be discussing about another method of measuring the burning velocity, that is flat flame burner method. In this case, if you look at a burner is designed in such a way that you can have a uniform velocity profile over here by using honeycomb, and this can be bundle of tubes, very fine tubes, generally hypodermic stainless steel tubes are being used, which is quite difficult to manufacture. And beside this, porous sintered metal disc can be used. In this case, there is also the cooling passages are being provided, so that you can cool this portion to stabilize the flame. And beside this, there is a provision is being made here, as I have shown here, to dilute the to create a curtain with the dilution gas, such that there will be no interference will be coming from outside with the flame. As a result, that this one dimensional flame is being established, and sometimes people use also the metal mesh to stabilize the flame, such that one dimensional flame can be established. In, of course, you need to supply the fuel air mixture to this burner. So, with this provision, one can really manage to establish a one dimensional steady flat flame burner. So, for this, as I told, that one dimensional velocity profile is to be established, and either using a honeycomb or a metal porous plug, and this inert gas curtain has to be provided, so that the edge of this one dimensional flame should not be affected by the ambient or atmospheric air. And as I told, the grid is being used to stabilize the flame, and in this case, as the flame is one dimensional nature, you can take the photograph of this flame, and then by carrying out a mass balance, one can really find out the flame burning velocity, laminar burning velocity easily. If you look at the mass balance, let us say this is the velocity which is going, and the flame is propagating with the same velocity SL. So, if you look at, this is the velocity which is coming. So, if you take a mass balance, you will find rho u A f, you can assume this the flame surface, this is your A f is same as that of the tube diameter or the burner. So, that you are considering only this portion A f, and V is the velocity of fuel air mixture, and which is does not vary along the radial direction, is equal to rho u A f S L. This S L is the laminar burning velocity. So, therefore, this is cancel it out, A f will be cancel it out, you will get V is equal to S L. So, that it is a very simple method by which you can get velocity very easily, because you know the mass flow rate of the fuel air mixture. So, V I can get the basically the volumetric flow rate of the mixture divided by A of this is your area. This area is basically known as the area of the burner, this area of burner. So, that by this you know this thing Q dot M, that is the volumetric flow rate of mixture. So, very easily you can get this thing, and then that is nothing but equal to the laminar burning velocity. So, flame area is interestingly is same for all methods like visible, shadow or silent photographs, because of fact that it is all remaining the same place. So, there is no change in the gradients, density gradient, and it is one of the simplest and most accurate method so far we have discussed, and therefore, it is being used routinely. But the problem with this kind of burner that it is not suitable for mixture having low burning velocity, and people of course are devise it further of using cooling passages, so that you can establish the flame even little bit lower than the 15 centimeter per second. So, but it is difficult to manufacture this burner, flat flame burner, because I had done this thing earlier. It was really very difficult, because I had used some kind the hypodermic tubes, and which will be getting blocked very easily, and once if some of the passages are blocked due to the dust in the fuel air mixtures, then you cannot really get the one dimensional flame because of change in the velocity at a local places or at locally. So, therefore, one has to be very careful of using this burner. So, let us now look at basically effect of equivalence ratio on the laminar burning velocity. So, as I told that one can vary this fuel air mixture in any of these methods, and then you can get different laminar burning velocity. For methane air system, it is being shown here, the laminar burning velocity is plotted for equivalence in the vertical axis, in the horizontal axis the equivalence ratio is being plotted. You can see that these points are basically different experiments, and there is another set of experiment which can say there is a little bit variation, and the solid line is corresponding to the numerical prediction, and of course, the dashed line is another theoretical prediction which is not very good, but one can see here that these are the experimental data of laminar burning velocity, and this is conducted at 1 atmospheric pressure. It can be noted that this is your equivalence ratio 1, it is not, and the peak value is occurring somewhere in this zone, which is the peak value is occurring around something 1.05, and on the left hand side the burning velocity is decreasing. This is basically your lean mixture, and the rich mixture, it is also decreasing. So, if you look at equivalence ratio around 1.05 for methane air flame, the peak laminar burning velocity occurs. And let us look at for other fuel air systems like your acetylene air system, propane air system. This is of course your methane air system and carbon monoxide air system. This is basically C3H8, this is methane, and this is acetylene, and this is of course CO, and all with respect to A. And one can note one thing that for hydrocarbon like methane and the propane, the peak burning velocity will be taking place around equivalence ratio around 1.05, whereas for carbon monoxide it is something occurring around 2, and for C2AC it will be occurring around something 1.2. And one can also conclude from this data of laminar burning velocities that for hydrocarbon air fuels, laminar burning velocity will be varying from 25 to the 50 centimeter per second, except the acetylene air, and whereas for the unsaturated hydrocarbon air, the peak laminar burning velocity occurs at equal to 1.05, and for hydrogen air mixture, which is not shown here, but the laminar burning velocity will be or the peak laminar burning velocity occurs at equivalence ratio 1.8. And how to explain this is very important, because the per CO, carbon monoxide, acetylene and hydrogen air, the peak laminar burning velocity is occurring at rich conditions, right, unlike the hydrocarbon air or unsaturated hydrocarbon air, where the peak laminar velocity is occurring around equivalence ratio of 1, generally 1.05 or around 1, one can say. And we know from laminar burning velocity that SL is basically proportional to 1 by rho u, and rho u is proportional to basically molecular weight of the fuel air mixture. So, therefore, if MW molecular weight, this is your molecular weight, and when molecular weight increases, then what will happen? SLU will be molecular weight will be decreasing, or vice versa, that means molecular weight of the mixtures or the thing will be decreasing, the laminar burning velocity will be increasing. So, one can really explain that CO air mixture also the maximum occurs under fuel rich conditions. And you can explain this thing that for hydrogen air, one can say that because with the addition of hydrogen air, the molecular weight will be decreasing, so that you can get a burning velocity max or the peak burning velocity will be occurring at the reach condition. But for CO air, the peak laminar burning velocity data cannot really be understood so simply, which may be attributed to the chemical complex chemical kinetics, which need to be explored further. So, as I told that peak laminar burning velocity for hydrogen and C2S2 CO are quite different, and it cannot be explained in terms of simplistic view of the molecular weight of the mixtures, as we had explained in case of hydrogen air. So, just to summarize, fuel air mixture of different, like we given methane, the burning velocity at equivalence ratio is equal to 1 is around 40 centimeter per second, whereas C2S6 that is 43 centimeter per second, C3H8 45 centimeter per second, and C2S2 is around 140 150 centimeter per second. Hydrogen is around 210 centimeter per second. So, let us look at effect of oxygen concentration on the laminar burning velocity. Here I have taken the data of SL with air, and on the vertical axis, on the horizontal axis, the mole fraction of oxygen divided by mole fraction of oxygen and nitrogen, that is saying basically what is the percentage of oxygen on the as a oxidizer in the oxidizer. So, of course, this is very important because of fact that the people are now bothered about the NOx emission, and then also for efficient combustion system people are thinking of using oxygen, or they are trying to replace the nitrogen in the air with the oxygen. So, if we have taken the 3 fuel here, one is methane, other is propane and carbon dioxide, you will find that the effect is very much predominant for methane, because there is a, of course, if you look at it is all greater than 1 in this zone whenever there is a more amount of oxygen is being given as compared to the air. And for methane, the SL burning velocity is increasing around something 11 times, and whereas for propane the laminar burning increase around 8 times here, if you look at something around 8 times, or and carbon monoxide the laminar velocity increases by around 2.5 times. So, question is what is the reason for this change, and this is because of fact that whenever this nitrogen is replaced by the oxygen, then there will be a higher adiabatic flame temperature, and if the flame temperature is higher, then naturally the heat release not being consumed by the nitrogen, which is inert gas. As a result, there will be increase in higher burning velocity, and if you look at really this adiabatic temperature, let me give you some data. This is CH4 air, the adiabatic temperature by Kelvin, if you look at it will be 2210, whereas if I just use the instead of air oxygen, pure oxygen, then I will get 3030 Kelvin. And similarly, if I take this carbon monoxide air, the temperature will be 2400 Kelvin, and CO for oxygen, this is 3220 Kelvin. So, there is a lot of difference between the temperature whenever you replace air with the pure oxygen. As a result, this the burning velocity will be increasing. The difference in laminar burning velocity can be attributed to different effective activation energy because of the chemistry will be different, and also the pre-exponential factor of global kinetics between these two fuel and oxidizer system. That might be the main reason why there is a change in the laminar burning velocity. And let us look at the effect of initial pressure. And if you recall that we had seen this data of laminar burning velocity with respect to the equivalence ratio. Phi is your equivalence ratio for 1 atmosphere pressure, and this is for air system, and what we will be considering for this methane air system, and increase the pressure and see what is happening. Here if you can look at the peak value of laminar burning velocity is around something 38 centimeter per second. If you look at this is something 38, and which is occurring around 1.05. And when you increase this pressure to 5 atmospheric, the peak values also occurring at the same location, but however, it has been reduced to something around maybe 18 centimeter per second. And when you increase this further, then to 10 atmosphere, the curve is similar, but there might be little bit less data here, and then nature is little changing, but however, the pattern of the variation of laminar velocity with respect to equivalence ratio remains almost same, only the peak value is being reduced. If you look at now, it is around something maybe one can say around 14 centimeter per second, and if I increase to further 20, then it is not changing much. If you look at twice, I have changed, this is around something maybe 10 centimeter per second. Now, question is why it is happening? That means, with increase in pressure, the laminar burning velocity is decreasing. In some cases, you may find that it is not really changing much or changing at all. So, that is a different situation or different fuel air system one can think of using. But let us look at that why there is why the laminar burning velocity is decrease or change due to the initial change in the initial pressure. We know that laminar burning velocity is basically proportional to the density and also the concentration. We had derived a relationship earlier, that is 32 by 9 alpha by rho u nu plus 1 m f average, this is half, this is basically root 2. We know that this mass burning rate of the fuel of average can be modeled for using a single step chemistry, that is MWF, AF, that is pre-exponential factor, and CF N1, C oxidizer N2, and E by RUT, the E is your activation energy. And we know that CF is basically proportional to, if I take N1 is the density of N1. So, I can say that then SL is proportional to 1 by rho u rho into rho N1 plus N2 power to the half. So, I can say SL is proportional to basically rho, and this I can say as N, this is basically rho N minus 2 divided by 2. So, N is basically the order of reaction, and if N is around let us say 1.6, I can say that SL is proportional to P because rho is proportional to P, n by divided by 2 is proportional to SL P, 1.6 minus 2 divided by 2 is P SL is something around maybe 0.2. So, of course, these values of 0.2 which may be varying. So, what is saying that if P is increasing, then SL has to decrease, and with of course, the coefficient of the 0.2 or it can be anything. So, I can say that SL is basically P power to the m. So, these values will be different for different cases, and then so that the burning velocity will be decreasing with respect to pressure. Of course, in certain range this n order of reaction will be changing. So, this if is order of reaction is changing, if it is happening, then the burning velocity will not be affected by the pressure or initial pressure. Thank you very much. We will stop over here.